So good morning and welcome to the second lecture where we're touching on what does sustainability means. We're looking at the technical, economic, and environmental perspectives to assess nano and bio-based projects. My name is Luana Dessbesell. I'm a professor at Aalto University, and I want to once again thank the organizers of the CG&B event and welcome all of you to today's lecture. So today, what I hope that you take home from the lecture is having a basic understanding of market analysis and how we can help us to define the potential of nano and bio-based technologies. As well as we will draft a process or block flow diagram, and we will have enough knowledge to at least take a look or make considerations about potential feasibility of these chemical, biological processes to make nano and bioproducts. The key focus of today's lecture and the subtitle, we can say, is translation of research into commercialization. And we are going to do that and describe that and exemplify that in two ways. We're going to take a look at some basics about a market analysis and bioproducts innovation. So why is it important? Some preliminary questions we should be asking, some basic definitions and some take-home questions. In the second part of the lecture, we're going to take a look at how do we take our lab results. I know some of you might be an undergraduate, some of you may be in a graduate program, you will be at different levels of your research career or your industry or government-based research or other types of backgrounds and work. The second part is about how we translate laboratory results into processes. So how do we make a block flow diagram? How do we see within that block flow diagram, what are the CAPEX items, what are the OPEX items? So basically capital investment and operational investment. And then some take-home questions about that part. So it's a very complex part of the technology feasibility studies. However, here we are just touching on some key aspects that I think go to enough of a level of detail for this about 50 minutes discussion we are going to have. I have shown this to you yesterday in the lecture. So we were talking about yesterday on how we have our current business, then we do some strategic planning in the long term, and then we transform. We make new products, we change our processes, we create just what we call this innovative bioeconomy models, so we remain competitive. And part of the bioeconomy model is a technology plan, the environmental analysis, and the business plan. This whole thing is basically a year of courses. But today we are going to touch a little bit in the first 30 minutes into the business plan. Specifically for the business plan is the market assessment part. So why is it important that we build these innovative business models? And why do we look at the technology and the business plan? It's because the technology evaluations, they inform the business plan. And then through the business plan is where we get information to make decisions and we identify objectives and gaps and what we want to be when we grow up. And then we go back to the technology evaluation. And it's really a feedback loop between the two, and they're very equally important. This is an overall summary of what if we had a document, which is a business plan, of what would that look like. So of course, we have a summary, we have a business overview, and then we have the market analysis. And that's kind of what we are focusing on today. It's where do we position in the product? What type of product are we aiming to make with that technology? And depending on the product, there are different characteristics. So, and there are categories of that we're going to touch today. And then there are many other things that we can look into as well. But I want to start, and I hope you have had breakfast already, because I put a picture here of bread. I'm really, I wish I could just, take a bite from the figure. But why is market analysis important? Imagine if you were very hungry and then you go to a grocery store and you see all of this amazing bread. You're just going to buy like crazy because you're driven by you're feeling at the moment, and then you're like, but then you still not to decide, even though you know you're hungry and you need to buy bread. And then you might look at the different types and what do we want to buy? Do I like more this type or that type? Each one of these have a different value proposition, depending on the time of the day. It depends on, you know, if you're gonna eat on the go, how we say in English. So we eat as you were walking somewhere else, whereas breakfast, which is you're going to take it home, slice it, toast it, and eat with something. So each one of these have unique attributes. In my look, they're all bread, but they have some different ways of making, target consumers, the time of the day. Each one of them were made in a different process. Some of them are made during the day, and they're all sold out during the same day. Some of them last longer. So each one of them have unique value propositions. So we want to understand, so which type of bread should I be making? Is it worth pursuing? So I'm making this new type of bread that no one have heard of. So let's try it. Maybe we need to give it some free samples until people get used to and understand if this is good for what and what to eat, what moment during the day. What is unique value proposition? Is that something really soft that melts your mouth, or it's something harder that you want to eat with soup or something? What is unique about that? Is it the nutrition of that is unique? Is it that it has low carbohydrates? Is it that that has no sugar, no gluten? So there are different things that make something unique. And what is the strategy for me to sell it? Like I mentioned before, should I give it some samples free? Should I heavily market it? Should I, before I even start making it, to get these contracts going so I know what to sell and I have a predicted future demand? So really, why we talk about this blah, blah, blah here about breads, but this applies to every type of product. This is very, very important in the bioeconomy, because it's very important to understand the market knowledge when we are planning on implementing a new technology. This graph is kind of heavy, but here you can see the degree of maturity and familiarity that we have with the technology when we're developing a new technology, a new product. And here's the degree of technology familiarity. So how much we know about technology, how much we know about the market. When we are making a bioproduct or nanobiotechnologies or like new products, we know very little about the market. The success rate, because we know very little, is very small. And the time it takes to commercialize is very high. And I'm not the one saying this. This is from a book, but it has been the subject of tons of papers, that it's very hard for us to create new value chains, to add new products to the market in the bioeconomy, the circular bioeconomy. And even if we know the market, we are replacing something that already exists, for instance, the time to commercialization is still high, especially you usually using a new technology. So the nanotechnologies are new technologies. So even though if you're replacing a product that already exists, that we know the market, the technology is new. So that technology uncertainty makes it the success rate to be lower, and the time it takes, especially the time it takes, should be higher, because we need to overcome all technology risks that we talked about in the previous lecture. So basically, this is just to give you an idea why it's so important to know about the market, because we talked about the technology risk in the previous lecture. Now we're talking about the market risks as well, and how do we look at the market? How do we know what types of products we are making can help us to minimize the risk and to accelerate the time it takes and to increase the success rate of bringing new products to the market? Then we should be thinking beyond the end final market. Oh, okay, I'm making these nanomaterials for agricultural applications, maybe, or electronics, or textiles, or construction, or food and water nutrients can be related to agriculture. This is basically this is a picture taken from the European Commission Action Plan, and they talked about these different value chains. Food and packaging, batteries, vehicles. So sometimes we researchers, we feel very comfortable on saying this technology is best suited for agricultural applications, for packaging. It's like a coating, is like a water filtration systems, or is replacing plastics, or is replacing some special mineral that goes into batteries or something. So, or is a carbon fiber for cars. So we keep it very high level. And we don't go into the detail, but if we don't go into the detail, if we think about, the need of composites in the car manufacturing the market is showing a steep growth. So in the future, there will be a lot of need. But sometimes that growth is driven by specific parts of the car that have very specific needs, specific niche markets, specific players that are making these parts, specific value chains. So just knowing what is the overall end use, the bigger market, is not enough when we want to see how likely is that the technology is going to succeed. So it's very important that we think about what is the supply chain, what is the value chain. This lecture, we are going to be focused on the value chain. So I don't know if you know what value chain is, what supply chain is. So I'm just giving you here a definition of what is the key difference. And it's pretty easy. Value chain is about the flow. So as a forester, let's take an example. We cut the logs in the forest, we cut trees, we have logs, we bring it to a yard, then we bring it then we might debark it, then we bring it to the mill, then in the mill we process it, then we bring it to the consumer, or we make it to pulp, depending on what you were doing with it. And so it's about the flow of things, of raw materials. And then the flow of money coming back. So when I sell it, the money comes back to me, and the flow of information that go back and forward. So the humidity of that log at the forest, after I debarked it, after it was stored in the wood yard for some time. So this is about data. This is about the flows of things. Then when we think about the value chain, and then here when we're talking about market, we are talking about value. It's the steps that add value. So when we go and we buy a tree from a farmer, we are paying the farmer for that tree. So we add value to that. Then we take it to the mill, we process it to pulp. We are doing one extra process to add value to that, right? We wouldn't be doing that process, we would adding value to that. And then we go and make that into paper, then we add value one more time. So it's about the value chain, the steps it takes to add value to something, to make into a product. Here is an example for you. And this is to a sectorial level. So we think about the fossil value chain. We keep talking about that. The products that we have, we're making out of renewable resources, such as trees, agricultural residues, waste streams, is going to replace fossil-based products. So this is one example of a fossil value chain. So is a value-creating activities. And then we start with fossil-based feedstock in this case, and this comes from Sarnia in Canada. This is an existing, actually, value chain that they have there. So we use fossils, we make energy, we do a further processing, we make chemicals, we do a further processing, we make polymers, we do a further processing, we make the packaging. This bag, for instance, a package out of it. And then we make a final product that comes to the consumer, us, and then we have some perhaps advanced manufacturing that we make further processing, and then it comes to us. This is a very simplified value chain. If we want to think about circularity, we would, and then after the consumer, there is end of life management, which can be recycled, landfilling, upcycling, and all of the 8 R's that we have. And then, it goes back at some point to Earth. So this is the idea of a value chain, is adding value. Then if we want to take that same value chain, that's what they have done in this location called Sarnia, which is what they call a hybrid chemistry cluster, is that this exists. So how do we plug in some bio-based products? So they implemented some new biorefineries that are using agricultural. This is a heavily agricultural area. And they are making new bio-based products such as succinic acid. They have some lignin extraction. They are making ethanol, biodiesel. And then as you go in this direction, we have more value. Closer to the consumer, usually, the closer to the consumer your product is, more value is added to it. But you see lignin here, which can be used for energy production. It can also be used to make finished products, to make plywood, to be the glue in the plywood, for instance, to make plastics, to make polymers, to make foams, and to finish a finished product, so the product that goes to the consumer. So basically here is like you see the value chain, you see points of entry that different products can enter the value chain once they are produced in a biorefinery. So this is kind of the goal of you understanding this idea of thinking of the product. Here we're not talking about the end use, we are talking about the actual product. We make ethanol, we are making butanol, we make biodiesel. Here we were talking about PLA that can be made into plastics. Here NCC as well, so other natural fibers that can be used in finished products, so even in composites. In this case, they make composites because they have a lot of car manufacturing also in that region. Then, why is it important to understand the type of product? So we were talking about the biofuels in the previous slides, for instance, because we have at least two simplified types of products. The ones that are commodity, the ones that are value added. Just keep it simple. For any type of product that we're making, there are two ways that we can compare them. One is how much we make, or there are several ways, but for the purpose of looking at market strategies and where the product sits in, there's how much we make and how differentiated it is, how far it is along the value chain, how many process steps it took to add value, how much value has been added to the product. So it's about the degree of differentiation. So it can be low or high. And then when we're talking about commodities versus value added, commodities are usually a large volume. They can be true commodities like biofuels or fuels, low differentiation. Liquid differentiation is low. Pseudo commodities, sometimes some grades of paper can be considered are pseudo commodities because there is a further degree of differentiation to that. But pulp, like crafted pulp, market pulp, is to most extent considered a true commodity, very, very large volume. And then fine products, they have a lower volume, but they're not very highly differentiated. And we're going to see examples later on. And then the specialty products are those things that are made specifically for that end consumer, that are very much differentiated in a very small volume. And each one of these, they have different strategies. If I'm on the top here, if I'm working with commodities, I want to be cost competitive because I'm making a lot of it. So I have economies of scale. I'm making a lot. I need to leverage what is internally, all of the CAPEX, the capital cost that I have, the assets, the buildings, the whole mill. I need to make the most with what I have. And I want to maybe store some, I can control the volatility of the market. I want to use different supply chain strategies. I want to have maybe even own a dock in a distribution center, or where I can really control and have my own supply chain stock or storage, where I can play when, okay, the prices go down, but I've already shipped a lot of pulp to Europe. So, I can still get this lower value and sell now at a higher value, for instance. And if we're looking at the bottom part, which is more fine or special products, is first to the market. You want to secure the market. It's not about selling it a lot to larger consumers. It's about having the right product to the right consumer at the right time. It's very much about differentiation. It's about how does my chemical fit into this specific client value chain. It's about arriving at their door at the right time with the right product that works for them. It's a very niche market. So you might have many small contracts of small volumes for many clients. In the top here, it's large contracts, large volumes to core clients most of the time. So these strategies are completely different. Think about our bread. Think about those breads that we buy in the grocery store that can be in our home for 30 days and they all bad. This is, to some extent, a commodity product, though those fresh croissants, or I don't know, pronounce in English or French or Portuguese, but or you know, this bread that we like, that we, or even like in Brazil that we like, the depending where you live, like the French bread. That we, the best thing is to go be the first one at the bakery and get it fresh. This is a niche product. This is something that needs to be made during the day, that each different place you go, it might taste different. Now, about push and pull. Depending on the product you make, there might be different reactions from these agencies, these people, these industries in the value chain, from the consumers at the end of the value chain, the producers on the other side. So if I push, which is the contrary in Portuguese, if I push in English, is that I think someone wants to buy it, so I make it. I forecast, I think that in the future someone is going to buy it. So it's more proactive. I make things, now I'm going to try to sell it. Then if I am responding to an order, someone knocks at my coffee shop and say, I want a cappuccino. And I'm going to go and make it a cappuccino fresh, because you cannot make coffee in advance. You could, like, filtered coffee and keep it in a bucket, and you know, but it's like a special thing. So I make when people come and order, or a sandwich. I want that sandwich, but I want you to remove the pickles, to do this and that and that, a special type of sandwich. So it's more a reactive process. Someone asks me to make it. One of a kind, I see special order that I'm not going to make the same style. So the pull is usually, there is reactive, someone orders it, but it gives you some time to make it. And you know you're going to be making the same type of thing, so we have the same ingredients. A one of a kind is something that is specific to that application, to that client, that you can make a significant number of changes in the process of making it. So if I want to make a rare type of shaped type of, the 3D printing can be something that's very flexible to make a one-of-a-kind thing. Arts also make a lot of one-of-a-kind things. But in chemistry, we can also, to some extent, make a one-of-a-kind thing. We can deal with the pH of a chemical. We can deal with the solubility of a chemical and make, or even those ionic liquids that we can make specifically for one type of application. And then we don't make them again, because we just wanted to test them to see if they would work. And if they work, then they become a product that's going to be made into continuous for volume. And this, I want to use, this is from MIT, the School of Management of MIT. And this is the idea of, you're going to see those acronyms later on. This is the idea of make to stock, make to order, and engineer to order. So you really change the process. And now let's take a look at the rest of this part in different types of examples, right? So we need examples, we need to understand. So we are talking about true commodities, large volumes. So we have very well-known specifications for those. So we can make them all the same way. It's a large group of buyers. The price is the most important thing here, that we would like to make it continuous, make more and more and more and more, instead of, you know, make a little bit, then change a little bit of process, make more. It's not about campaign making in the mill. It's about making it continuously. It's making it in volume. So we use a specific, it's make to stock. We stock biofuels. We have a stock of things. So of course, not forever, but we stock, we make, and we can store and sell it when there is the most favorable market conditions. And we can forecast demand. We know how much people usually use of biofuels or fuels in general. And these are some examples. Then if we think about the pseudo commodities, and here I have a roll of toilet paper, it's large quantities as well as commodities, but they're sold according to performance. So to some extent, the different layers or the different, how do you say, granage, I guess, I don't know, like the thickness or the different characteristics are made specific for different types of consumers and markets. So there are different grades of pulp and paper made for those. So this can be made to stock and can be made to order, depending on the few large customers that exist. There is some type of customization, often at the end, when I'm finalizing the product, I do that customization. And there's some grades of plastics, other paper, pulp and paper products. P and P is pulp and paper. Now, one more example on that is the fine, we can call them fine chemicals, fine products. And those are lower volumes, as we mentioned, they're at the bottom of that graph you saw. And there's a smaller number of customers, and these are campaigns. So it's made to stock, but it will make and you stock, and then you deliver to the client. They're not made to order, they're still made to stock. But they have a very precise chemical structure. So it's something that the client needs, that they tell you in advance what they need. You make, you stock, and then you deliver them at the right time. For instance, a lot of food chemicals have a very specific chemical structures that my process can make a volume of this food additive. For 3 months, we make this food additive, and then we store, and then we sell to the specific customers. Then for 3 months or for 3 days, we run a slightly different process, and then we make a different type of a food additive or pharma additive within the same meal that is for another client. So the process needs flexibility, but it is a fine chemical. It's something that's very specific and unique. And then we have the specialty ones, which is the last category. And of course, there are some overlaps and merges among them, but this is really make to order. I knock at your door, and I want you to make something special for this new type of product that I'm making. So it's very small quantities, is according to consumer specific characteristics. You have several small volume customers. It's about scheduling. It's about delivering the right time. It's about efficiency of the supply chain. And it depends a lot. So sometimes some dyes and pesticides, some materials, especially those high-end materials, or conductive textiles, or things that are made very specifically for this consumer to test in new advanced materials. They usually are specialty types of products. This is a big summary for you as we're finishing this first 30 minutes, where you can kind of see in these boxes, which is kind of messy, but if you want to, at home, pause this video, take a look further, have an idea of what each one of those have and how to differentiate them. This is a good way for you to take a look. And then as a summary slide is that, now, how do I do this market analysis? First thing, figure out what your product is. We don't have time to do that today. You have some examples. What your product is. So if it is commodity, it's very competitive business. Price is very important. And I need to make a lot. And I need to really maximize my capital expenses. And I need to be very efficient in the supply chain. If I make a specialties or added value, it's less price sensitive because usually they're very, very higher price. So the price doesn't fluctuate a lot. Is about differentiation, is about being competitive, is about controlling the specific market for that very niche type of product, and is about responsiveness, is about being able to respond to the need of your client, which can be, make to order types of products. This is the summary of this first part. We have reached the 30 minutes that I have planned for this part. What should you be asking to close this? When I'm doing a market analysis, regardless of the science, I shall say, but especially if we want to look at the early stage, very early stage, we're still a lot. We need to think about what is the potential, most promising final application, and not just the value chain, not just the end market, application, final product that we're going to be making. Is it paper? Is it, a coating that goes into a bottle? Is it the new type of dye that goes into textiles? What is the value chain? Who is making it? For what? Who are the players in that value chain that we saw as an example? Where am I entering the value chain? Am I making a precursor to the end product? a chemical that is going to be making to a plastic bag, for instance? Am I making the plastic bag myself from bio-based resources? And what is the unique value proposition? Remember about the brand. Each one of them have a unique value proposition. The product you are working on also has a unique value proposition. And that should be thought of social, environmental, economic. So the whole sustainability of the value proposition. Now, let's dive right into part 2. So that was a lot. Part 2 is a little bit more technical, less of this broader market perspective. And it should take just less than 10 to 20 minutes. So now how do we translate? Now we're developing these things in the lab and we need to turn them onto new things, new products, new processes, so that they finally at some point leave the lab. In this case, again, I show that figure, and then we're going to focus now on the other side of the thing, the technology plan. And inside of the technology plan, more specifically, we are going to look at this part of the full report of a technology plan, which is creating this high-level block flow diagram. Remember, we are at early stage technology. We are not yet, the engineers that have built something that are preparing a pre-feed engineering package. We are at a very early stage. We are at remember we talked about technology readiness levels in the previous lecture. So we are at the technology readiness level, perhaps 3 or 4. We are still very early. We have maybe thinking about the pre-pilot, but we can look at the lab results and create this block flow diagram from the lab results. And then when we have the block flow diagram, we can think about, is it feasible? Because when we create a block flow diagram, we can see, I need to precipitate this product here. I need to use this different type of solvent, and then I need to recover the solvent. Okay, there's a recovery system there. Then I need to grind the product in the end. So there's a grinder. Then I need to dry the product. Then there is a dryer. Remember, we talked about the technology readiness level in the last lecture of non-related cellulose and how the drying, depending on the process, could be a very low TRL, even though making nanocellulose was not. It was already a commercial scale, and how long it takes to just figure out that one part of the process. And at the same time, you need to figure out the technology part and the economic feasibility part of that process as well. And because you need that process to work, you need those characteristics for your end product that you did all the market study. And at some point, you might get to the market study and then come back and say, no, that's not the best application. So let's review the process. Let's review the block flow diagram. Let's see what's needed now. Now we are looking at a new application, so I don't need the drying anymore. So all of those feedback loops are very important. Whew, this is a big one. This is a busy slide, so I'm sorry in advance. But what is a block flow diagram? We might not be all engineers here, so what is this thing that I'm going to start calling BFD? So block flow diagram. It presents the flow of equipment and plant processes. So what equipment and what processes happen, what goes in, what comes out. And then I want to show you this example that I visited this is a lignin extraction plant at the top here, the figure. And I went there and I took this picture. Now, I don't know if this is my picture, maybe. This part here is for sure from presentation from the responsible for running the plant. This is lignoforest. This is a technology developed in Canada by AP Innovations, which was built at commercial scale by West Fraser, which is a symbol of this company, which is a pulp mill in Hinton, Alberta, in Canada. And I went there, I took a couple of pictures, not sure if this one is mine, it looks so nice to be mine, but I have one similar. And then like what I knew about the process before going there is what is here, what I have worked with, I have looked at because I worked in this in my PhD. And then when I went there and I actually saw the thing built, I was thinking, oh my goodness, I mean, where is what? I was thinking, okay, I can maybe think that the biggest thing there maybe is the precipitation tank or the coagulator, or the, you know, like I was trying to see where the things in my drawing that I drew, I've seen my colleagues drawing, were in the actual real plant. And then to give you an idea, in reality, this is what look on the paper. In reality, these are the reactors. So this is the coagulator there, right? There you go. So I think it's the only thing that I actually had an idea and then I saw it. And then basically, this is the press, the filter press, this long part here. So, and then at the end, they kind of have like two different types of lignin that are used in resin applications and as an adhesive, which lignin is the glue of the trees, right? So they are extracting and using for different applications. It even using within the mill because the mill has a plywood mill on site. But the thing is, the main point here is like this process was done in the lab and then it was done at a pre-pilot. And this is a commercial scale plant. It's 10,000 tons a year. So when you draw things, it looks so easy. When you build things, there are so many things involved. And this is all very important to consider when we do the mass and energy balances and when we look at what each part of this might cost. And then I have here another example, and this was actually my PhD work. So that's the thing, I saw that process before. So that process you saw on the previous slide was coming into this one. So I had this is basically ends there, the previous slide, and then it starts here again. So the lignin that were coming from that process, we were using a conveyor, bringing to a reactor where we added a few other things that we would depolymerize lignin, and then we would separate the lignin and then make that into, of course, recover all the chemicals and make that into I would call it polymer that can replace 80% of phenol and phenolic resins, because without modifying the molecular weight, I'm going to too complex here. But anyways, we need to break it down, the molecule, so that we could use it more. And the whole idea was that we add this further step into the previous step, and we can sell more, replace more, and there was a need for the market. And then at that stage, they were only replacing like 40% or 30%, or even 15% in some cases, depending on the pH of the lignin, that we break it down, the molecule could replace more. So that was what I was studying in the lab and developing the pilot for that process. But this is basically what it can look like. These are different pieces of equipment with different feeding lines, which had a whole mass and energy balances behind. Then when we go into, this is what the mass and energy balance means. So it's a flow of equipment. This is what you saw before, but it's also about what goes in to what flow rate and what comes out of it. So this is, don't worry, like this is too much detail, but this is basically what I want to say is that we had only lab results, and we were able to transform the lab results into actual processes, and then validate in the pre-pilot, and then go back and redraw and see how much it would cost if we were to scale up that process. So basically, it's very important that we draft, that we look at the mass and energy balances, that we know what pieces of equipment go where, how they are connected, how we're going to recover the chemicals, is it possible to recover, so that we can see, again, risks. And we talked in the previous lecture, is about identifying the bottlenecks, is about identifying where in a process there can be challenges, because then we do all of the sensitivity analysis and all of other studies, which we cannot cover today, to see, oh my God, if I don't recycle the acetone, if I don't recycle the solvent, what happens? Then my process is not feasible anymore because it's too expensive to add more new fresh solvent. So I should be able to recover 98% or 80% or 100%, otherwise it's not feasible. So it's possible then to compare with what other processes exist. So when you were designing a process, or you're creating a new technology, or you're producing a new nanocellulose type of processes, any type of nano or bioproduct, you need to benchmark with existing processes, because that will help you to identify in that previous figure, for instance, does this type of reactor exists? What is the interactions between the product I'm putting in and the actual coating that needs to go inside of the reactor, for instance? Is it possible to recycle acetone to the rate we were hoping to recycle it? Can the water be reused? So all of these things come up in your mind when you were doing the mass and energy balances and you were drawing the drawing, because in the lab we are making things in a very small, like I had a 500 ml reactor. That doesn't at all relate to what is going to be in reality. And what's the capacity? How big should it be? And then, for instance, we were vacuum evaporating the acetone. Of course, that's not how it's going to be done in a larger scale. But in the lab, it works. So in the lab, you might have the minutes, the time it takes for you to do it. But in larger scales, how long it's going to take for the reaction to happen, the temperature is going to be used, the type of equipment is going to be used, it counts. It makes a whole difference. And it will impact then the yield and the quality of your final product afterwards. So it helped us to see what is the equipment, benchmark with other processes, what equipments are available already. And now we know the application, we know at the end of the process what we were looking for. So we really can see what is available, what is missing, look for costs for the similar processes that use similar equipment, look what size they have been built, what hasn't been built yet, what are the risks, and it helps us to estimate CAPEX and OPEX, and that's very important. But do you know what CAPEX and OPEX is? Do you have any idea? It's all fine. I mean, we don't use those very often, but I'm just going to give you a definition that comes from textbook. So it's about the CAPEX expenditure. So it's the cost of pipes, valves, fittings. So you saw that drawing, or you saw that other photo of the process. It's all of the things that that something flows inside. It's all of, the physical things, compressor, turbines, whatever construction is needed. So is in simple terms, if we want to make it simple, is the things that the capital, the amount of cash, the capital we spend to buy, install, and maintain physical, something you can touch, physical assets that will depreciate over time. So if we take that block flow diagram that I showed you earlier, you'll see here that everything that is highlighted in yellow here is a piece of equipment, including the piping that connects them, that are part of the CAPEX. So the capital expenditure, remember that, is things that you can touch. There are physical things that depreciate. And then the other side of the costs is usually called operating expense, OPEX, operation costs. And these are things that we need to run the business. So things that often include rental, if you need to rent something. Inventory basically means you buy all the raw materials and you store raw materials, or you pay people, you pay insurance, everything that is related to run the business. But when we are in chemical processes, bioprocesses, nanoprocesses, nanotechnologies, we are looking at things that everything that varies with the amount of product that you make. The reactor has its capacity, so we are making the full capacity of the reactor. But I mean, reactor cost is going to be the same if I make less of the product or if I make the full capacity of the product. It doesn't vary depending on the amount that I make of a product. However, if I want to make more product, I need more feedstock. That varies if I want to make more or less product. So we need to ensure, it's basically every cost that we need to ensure every day, that we need to make the product every day to keep the process, the mill running. So if we take that image again, the green things are like water, oxygen, CO2, again, here, all of the things that are coming into the process. So things that I need to make at the end of the day, in this case, a precipitated lignin. So this is what we call OPEX. Now, to kind of exemplify from that paper that I showed you for my PhD work, when we put these two pieces together, the top here is a process, which pieces of equipment in CAPEX. This is the mass and energy, is really the mass flow. The energy balances is in another table. But here is just for you to kind of have an overview. We put these two together. We can come up with, in this case, we were making like 3 different processes into different mixes. The best recipe for replacing polyol, the best recipe to replacing phenols, and the best recipe for replacing polyol with an extra step. And then it's how much it would cost to make it. But I don't want you to really focus on the details. It shouldn't even, this graph is awful now that I look back when I did this PhD thing. A graph should have been done much nicer, but it's basically, water is a OPEX, the reactants is an OPEX, linear depreciation is its own thing, it's related to the CAPEX, how much is on top of the CAPEX. Sodium hydroxide is again OPEX, acetone is OPEX. The total project investment is also part of the CAPEX. Utilities is part of the OPEX. Fixed operational costs is part of the OPEX. Ethylene glycol was part of the OPEX, and kraft lignin is part of the OPEX. So basically, if we can break it down into little things, but basically you see that the raw material is the main cost here. But when we put this all together and we just categorize between 2 things, we are talking about operating costs, which usually take most of the costs, and then the capital. You usually want not to have CAPEX too high and have the OPEX. So this makes, for that case, an average selling price of the depolymerized lignin would be 1,420. But that's so there's a lot of uncertainty in that result. But just to give you an idea of when you do a cash flow and then you have the OPEX and the CAPEX items, then you can come up with a price per ton or per kilo or per unit of your final product. So you need to know the final product, you need to know CAPEX, you need to know OPEX, which is mass and energy balances. You need to know what parts of the process are more energy intensive. You need to really have an overview of the entire process to be able to come up with the price of the product. So some take-home messages as we close this lecture with regards to the part 2 with the large block flow analysis is that basic questions when we are in the lab and we want to draw a block flow diagram and try to come up with some CAPEX and OPEX is that, can we do it based on literature? Not just only our result, but whatever else is available in literature. So we might say, no, we can't. We need to do further studies. We need to collaborate with industry. We need to find other people that have done this process before. Then we identify what information is missing, who we should reach out to, who is in the value chain, who is making this product, what is the current selling price of the products, what are the most important process risks already from early stage, just from the gaps we identified and from the parts of the process that have a lot of unknowns. And then what are the main costs? What are the things that you can put like a red flag? These things need to be well developed because these are the core costs. In the case, the previous one was actually the cost of the kraft lignin after precipitation. And then other costs were related to actually the recovery of the solvents, for instance. Then we are able to see what are the red flags. So this is what I want to leave you with, is that we should know what's the end product, who is making it, how, and what are the strategies for developing this product and selling it. And then when we think about our process, where are the main things that we need to de-risk? What we know, what we don't know, and can we look at and have preliminary CAPEX and OPEX estimates? Thank you so much for today again, and I see you tomorrow in the last lecture where we're going to touch into the term, how do we bring this whole thing into a sustainability perspective? Thank you. Have a great day. See you tomorrow.